Welcome. Thank you for the committee for inviting me to come and talk. I'm going to give you a quick primer or introduction to mechanotherapy and mechanobiology. And a lot of this work, or as a background reading, if we go a little fast today or you miss something, you can look at your physical therapy journal from April this year, which gives a complete overview, a paper that we wrote for the Regenerative Rehab special issue. And we all know that musculoskeletal tissues, and not just musculoskeletal tissues, but a lot of tissues within the body are able to respond and adapt to the mechanical environment. And that sort of makes sense, seeing as most of the tissues are being exposed to mechanical forces, and their primary role is to generate or transmit or absorb force. So it sort of makes sense that the tissue needs to be able to modify itself in response to those forces to make itself stronger, to renew itself. And if you think about the tissue level sort of properties that take place within the body, and you look at growth and development, and you can see this is a classical study in dogs. I'll disclose that most of my work is looking at bone and skeleton, so I use a lot of bone and skeletal examples. But this is a classical study in dogs where they immobilized growing dogs and mature dogs to look at what's the effect of immobilization on the skeleton. And you can see that in the growing dogs, that if you immobilize the young growing animal, they don't develop the normal skeletal structure of a mature animal. If you do it in the mature animal that's already established its bone size, then you get bone loss from the inside. And you can take this all the way back to embryology and also to in utero, that there's studies showing that if you don't mechanically load in utero, then you don't get appropriate skeletal formation. Your bones don't form the normal shape, they just form circular tubes. They don't adapt to the mechanical loads. That's growth and development. Modeling. Modeling is adding new tissue to a surface or to an organ. And in bone, when we talk about modeling, it's adding new bone to bone that was already there. So it's a quiescent sort of surface. You do some sort of stimulus, in this case mechanical loading, and you add more bone. It's not remodeling where you take away old bone and add new bone. This is just adding more material. And this is some of our work looking at baseball players, and you can see in the non-throwing arm of this player, this is his normal humerus. If you look on his throwing arm, he's basically doubled the strength of the humerus. So via mechanical loading over about 25 years, this person has actually doubled the strength of their skeleton. So it just shows the potent ability of mechanical loading to induce adaptation. Remodeling is taking away of old damaged tissue and replacing it with new tissue. And here another example in bone, we all have these areas of microdamage in bone. Everybody here has about 1 million areas of micro cracks within their skeleton, and it's thought that stimulates targeted remodeling. So from a Haversian canal, you get osteoclast creating a cutting cone that go towards that micro crack, resorb it, and then behind that come osteoblasts and replace it. So this is replacing old material. And then the last sort of tissue level process that we think of is repair, and you can say regeneration when we talk about bone, because bone is a tissue that regenerates. It replaces the old damaged tissue with the native tissue. It doesn't form a scar. And we know mechanical loading is really important here, because if you overstabilize a fracture, you don't get any callus formation. If you understabilize a fracture, then you get formation of excessive cartilage. So there's this sort of happy medium where you've got to stabilize enough to prevent forming even a pseudoarthrosis, but if you stabilize too much, then it won't heal. And people are trying to manipulate this process mechanically now with fracture healing to try and get fractures to heal quicker, and also to get non-unions to heal. So then you start thinking about, okay, if all these tissue level processes are affected by mechanical stimuli, then can we use mechanical stimuli as a therapy? and we coined this term mechanotherapy. And this is nothing new. If you look back at the tomb of the physician, Akmathar, that they were doing mechanical loading, mechanical stimuli way back, 2,000 years before Christ. And even Hippocrates had different sort of techniques for, he was sort of doing a lot of mechanical therapies. In this case, this is his rack for scoliosis. I'm not sure why the therapists are nude. It's sort of the alternative clinic, the way it is. But if you look in the literature, really the first definition of mechanotherapy came about in 1890. And it was the employment of mechanical means to cure disease. And I love the 1800s, 1900s, because you could basically just cure anything. I'm going to do this, and it's going to cure this. There's nothing in between. It's, okay, we're going to mechanically load a tissue, and it's going to cure you. And these are some of the devices. This is your medical gymnastics. This is almost the birth of physical therapy around the 1900s, 1890. And these are some of the mechanical devices that were made, and it was basically mechanotherapy. And you could go to the American College of Mechanotherapy. And it wasn't until 2009 that we actually changed the definition of mechanotherapy. So it took over 1,000 years for this original definition to be modified from, okay, let's introduce mechanical loading and we get cure. Well, what happens in between? What's the process from mechanical loading to tissue response? And so Karim Khan and Alex Scott at Vancouver published a nice review article talking, introducing mechanotransduction to therapists. And that's sort of the process of how we have mechanical loading and it results in a cellular response. So we've built on that, and Alex Scott was one of the co-authors on this paper, and basically, the definition that we're using, it's tying in the different components of mechanotransduction and the tissue-level processes, but it's introducing mechanical stimuli with the goal of altering the molecular pathways to get a cellular response to change those tissue-level processes, whether it be growth, remodeling, modeling, or repair. And it's really to tie in, so instead of just saying mechanotransduction, what is mechanotransduction? And we're going to talk about that in the next few. It's going from molecules to cells to tissue. So let's talk about mechanotransduction, or the mechanobiology side of things. And mechano means mechanical. Transduction is the conversion of a force. How to convert that force? This is working. Things are a little loose. The conversion of that biomechanical force in cellular and molecular response. And so you think about. Keeps cutting out. You got the other microphone? Let's use that. Is that better? There we go. So you think about mechanical stimuli, and everything we do in physical therapy, rehab, is basically a mechanical therapy. Right? Almost everything we do involves mechanical stimulation of tissue. That mechanical stimulation results in a tissue force. That tissue force is influenced by the properties of the tissue itself. And this is our baseballers. So this is the non-throwing arm. The throwing arm, you can see how much bigger and thicker this mid-shaft humerus is in this throwing arm. So we modeled forces during pitching on the humerus of baseball players. And this was the force or stress-strain distribution in the throwing arm. If you apply those same forces to the non-throwing arm of the same person, we just wanted to see, okay, how did that adaptation influence the forces in the tissue? You apply those same forces to his non-throwing arm, his arm would break, right? So if we put the same forces that a Major League Baseball player generates, if we put it onto your humerus, your arm would break, right? So they've adapted over time to reduce the stress and strains within the tissue. Those tissue forces then go and generate cellular forces, and they're influenced by mechanical properties of the cell. And we know that there's this feedback that when you load cells, and these are some bone cells, and being exposed to fluid flow, and the fluid's flowing from right to left. After an hour of fluid flow, you get the cytoskeletal arrangement or rearrangement within the cell, and it stiffens the cell, makes the cells themselves stiffer. So you change the mechanical properties of a cell by exposing it to mechanical stimuli. Those cellular forces then somehow create this molecular response. And that molecular response is what results in either generation or formation or degradation of the extracellular matrix, which then feeds back to change the tissue properties. So it's this feedback loop that you get adaptation. So this is just sort of mechanotransduction sort of pathway of introducing some sort of stimulus, whether it's intrinsically generated via skeletal muscle contraction, or it's extrinsically introduced by manual therapy, massage, or any other external mechanical stimuli. So let's look at this, breaking it down. You've introduced a mechanical stimulus, you get some sort of tissue force. The question is, how does that tissue force convert into a stimulus that the cells can identify with? And this is mechanocoupling. How does that tissue force then result in a cellular force? And cells are able to respond to all sorts of different mechanical stimuli, and different cells respond to different stimuli. And it could be tension, pulling on a cell, compression, shearing a cell, so gliding of different tissue layers, shearing on the cell, hydrostatic pressure, vibration, and fluid shear. These are just some of the examples of different stimuli that we know cells respond to. It might not be completely intuitive as to what cells are exposed to what stimuli. For example, if you think about tendons, and you think, okay, well, a tendon is designed to resist tensile forces, so therefore tenocytes embedded in the tendon must be exposed to tensile forces. Well, it's not necessarily the case, because as you contract and there's shearing of the collagen fibers, you get shearing or shearing of those tenocytes embedded within the collagen fibers. So you get shearing, you get tensile forces. Also, you get compression of cells. So as you stretch out the collagen fibers, the tendon actually reduces in cross-sectional area, and it compresses the most compressible thing within the tendon, which is the cell. Right? So it's not completely intuitive exactly what cells get exposed to what sort of stimuli. Then the cells need some way of transducing that stimuli, that cellular stimuli, into a molecular response. So they need some way of sensing that stimulus. And one way, the classical way, is the cytoskeleton. So the actin, sort of cytoskeletal, and well, basically it's the integrin cytoskeletal sort of network where the cells are anchored to the extracellular matrix. So you have these integrins that connect to collagen, and they hold the cells in place so that they're not just free floating, they're held in place. Those integrins are connected to the cytoskeletal arrangement in cells, and this is an unloaded cell, and this is a loaded cell. And some of the work of one of the colleagues at IU, William Thompson, who wrote the perspective with me, shows that these integrins, which are extracellular, they connect with the cytoskeleton within the cell, which then connects directly with the nucleus. So there is a means of stimulating a cell and directly affecting the nuclei of the cell to influence gene transcription. So that's one way that the cells can respond by pulling on these integrins, which pulls on the cytoskeletal features that then pull on the nucleus. But we also know there's a lot of other ways that cells transduce or convert that mechanical stimulus. There's stretch-activated ion channels within the cell membranes. There's G protein-coupled receptors that when you mechanically load, it results in a conformational change in the receptor that allows some sort of ligand to bind to it. There's growth factor receptors, and then the integrins. So you get this sort of stimulus that the cells are responsive to. Then you need to convert that stimulus into a biomechanical sort of signal. So how do these sort of signals then change the extracellular matrix production by the cell, or produce a signal from the cell that then goes to an effector cell to change tissue properties, to get an effector response? So if we look at, for example, these stretch-activated ion channels, the classical one is calcium, that you get an influx of calcium when you mechanically load a cell. And there's all these different pathways, and there's not going to be a test on this today. But you have this sort of molecular sort of process within the cell that calcium influxes and it changes CAMK, nitric oxide synthase. Nitric oxide goes into the nucleus and then stimulates these mechanosensitive genes. You've got G-coupled protein receptors. So you get coupling of the ligand with the receptor, and it results in a cascade of molecular changes within the cell that then goes to the nucleus to influence protein synthesis, or produce mRNA that then goes to protein synthesis, growth factors and integrins as well. So you have all these pathways, and it's probably, well, we know it's a lot more complicated than this, that we directly link these different molecules, but there's also a lot of molecules we don't know about. But somehow this mechanical stimuli triggers the mechanosensor that results in a molecular or biochemical coupling or cascade that results in a change in cell activity. So what does this mean? So somehow we've got this mechanical stimulus, the cell responds to it, senses it, changes cellular activity, results in a change in tissue properties. So as therapists, how do we use some of this information? Well, one way is, how do we determine we have this mechanical stimulus, whether it's intrinsically produced through muscle or is it extrinsically introduced? What sort of tissue forces does this result in? And we're making good progress in determining what external loads, what sort of tissue loads they create. And you can do it invasively. You can introduce transducers to tissue, and people have done this with tendons. They put buccal transducers on Achilles tendon and get people to exercise, and they can look at how far the tendon, the stress and strain within the tendon. But we're getting better at doing non-invasive means and doing musculoskeletal sort of modeling. And this is how we modeled the forces on the humerus on the baseball players, is you get motion capture. You work out the forces that are acting at, in our case, the shoulder and elbow. We work out three-dimensional, what are the torques and forces acting at those joints. In the same player, we get their muscle volumes, so we work out how big their muscles are. We plug it into a musculoskeletal model, which is based on cadaver dissection. It's the angle of pull of the muscles. It's the insertion of all the muscles. You plug in those forces and the muscles, and what you work out is what muscles need to be active and how hard do they have to contract to generate a force vector in exactly the same direction that we measured in via biomechanics. Right? So we work out, okay, if the force vector is going this way in 3 dimensions, what sequence of muscles do we have to activate, and how hard do they have to pull to generate that vector? So we work out what muscles are active, and then we plug those muscles onto a finite element model of the bone from the same person. So this is all subject specific. Right? We're doing their biomechanics, their muscle, and their bone. And then we apply those muscles to the finite element model of the bone, and you can work out the stress and strain distribution within the bone. Right? So we're getting better at working out what sort of strains and stresses we're introducing to musculoskeletal tissues. If we move along to the next part, if we think about, is there a way that we can introduce novel stimuli based on what we know how cells respond? And if I stick with bone, you've got all these osteocytes which form 95% of the cell type in bone. And historically, they thought they were just dead bone cells. They just sat there within the bone and didn't really do much. Well, how can 95% of bone cells do nothing? It didn't really make sense. And if you look at an osteocyte in scanning electron microscope, you look at all these connections from one osteocyte. It's basically a communication cell, right? And we now know that pretty much the osteocyte is a mechanosensitive cell in the skeleton, that it's sensing mechanical stimuli and it's relaying that signal out to the effector cells on the bone surface. The stimulus for how bone responds to mechanical loading is not stretching and it's not bending of the bone that results in stretching of those cells. What we think is happening, or it's pretty much almost proven, but without being proven, is that when you load a bone, you get a bending moment. You get compression on one side, tension on the other. And what happens is you get this fluid flow, or this streaming of fluid within that canicular network that the osteocytes are in. So you're getting these shear forces and stimulation of these osteocytes. So knowing that the mechanical stimulus for bone cells to respond to mechanical loading is this fluid flow, is there a way that we can introduce fluid flow to bone without actually loading the bone? So can we introduce this sort of fluid flow without actually loading the bone? And there's a couple of different ways that people have done this experimentally. This is a study out of Stony Brook where they put a pressure cuff on rats, and it was pumped up to 30 millimeters of mercury, static pressure, and then on top of that, they had a 30 millimeter peak-to-peak sort of pressure wave at 2 hertz. And what they found was that when you put the pressure cuff on and you measure pressure within the intramedullary canal, that you get this increase in intramedullary pressure. And when you get an increase in intramedullary pressure, what that's doing is causing the fluid in the intramedullary canal to push out through the canicular network where the osteocytes are. So by oscillating this pressure up and down, what they can do is get fluid flow across the osteocytes. This doesn't result in any loading of the actual bone tissue, so the extracellular matrix, but it's causing fluid flow. And when they did this, here's a control animal. Your hind limbs suspend an animal, so you take their hind limbs off the ground, they can get round on their front legs, they lose bone. If you apply static pressure, there's a little bit of improvement, but if you apply this dynamic oscillating fluid flow from the intramedullary canal out through the caniculae, it basically stopped bone loss. Right? So they prevented bone loss by stimulating the bone without actually loading the tissue per se. But by knowing the mechanotransductive sort of pathway, they were able to work out a way of inducing mechanoadaptation without actually loading the tissue. Whether this will translate to humans, we don't know, because it's very easy to load a rat and get an intramedullary pressure change. Whether you can get a similar change in humans to induce adaptation hasn't been shown. But it's a nice example of how understanding how bone cells respond to mechanical stimuli, can we manipulate that and introduce or develop novel stimuli? What about at the other end of things, the cellular forces to a molecular response? Well, the PTH, or parathyroid hormone receptor, is the receptor for parathyroid hormone. And parathyroid hormone is an anabolic agent for bone. We also know that this receptor is mechanosensitive. So if you co-introduce PTH and mechanical loading, is there beneficial effects or is there synergy between the two? Right? So does PTH sensitize this receptor to mechanical stimuli or vice versa? If you mechanically load this cell, does that enhance the PTH effect? And this was done by colleagues at IU, where what they did was use our ulnar loading model in rats that was shown before, the movie before, where we bend one arm in the rats and the other arm is the internal control. With loading, you get this nice adaptation within the bone. If you load and add PTH, you get this synergistic effect. Right? So it comes back to, if you've got a patient who's taking PTH, right? They're getting PTH injections for skeletal health. What we need to do is optimize our timing of mechanical stimuli, so exercise, so that it combines with the peak time of PTH, circulating PTH times, and that's usually about half an hour after the injection. Right? So if you're using exercise to enhance bone health, and this patient's on PTH, do the exercise 30 minutes after the PTH injection, because the cells are primed by PTH to have a synergistic effect with the exercise or mechanical stimuli. We can also use this knowledge of mechanobiology, mechanotransduction, the other way. If we think about COX-2 or cyclooxygenase 2, it's one of our early mechanosensitive genes. So when you load, whether it be skeletal muscle, bone, tendon, ligament, you have some sort of mechanical stimulus, you get an influx of calcium, a lot of stuff goes on here in between, but you end up getting an increase in COX-2 expression, cyclooxygenase 2. What does COX do? Why is it relevant? Well, COX-2, the COX enzymes convert arachidonic acid into prostaglandins. Right? They're the target of your NSAIDs. right? So the cyclooxygenase enzymes, when you get mechanical stimulus of a cell, results in collagen synthesis. And how this is relevant is that if people are taking prophylactic NSAIDs, so they're taking NSAIDs prior to their exercise, what they're doing is shutting down cyclooxygenase. They're shutting down a mechanotransductive pathway. And it's been shown in pretty much all the musculoskeletal tissues, muscle, bone, tendon, maybe not ligament yet. But if you take NSAIDs, or you introduce an NSAID to an animal 30 minutes or so before they exercise, it blunts or even gets rid of the mechanotransductive adaptation. Right, so taking prophylactic NSAIDs can actually prevent mechanoadaptation. And that's been shown multiple times in lots of different tissues. Right, so by knowing that this is an important mechanotransductive pathway, we can give advice about, okay, should we be taking NSAIDs and these agents that inhibit cyclooxygenase prior to exercise? A new pathway that's all the rage sort of right now is this LRP5 Wnt signaling pathway. And LRP5 sits on the cell surface, and it's inhibited by this molecule SOST. And when you load a cell, mechanical loading of a cell inhibits SOST. Right? So you do some sort of mechanical stimulus, SOST is inhibited, and it allows LRP5 to bind to frizzle, then you get this sort of altered gene response. Right? So this is an important mechanotransductive pathway that if you mechanically load, you decrease SOST expression, and you allow this pathway to take place, and you get adaptation. So by knowing that this is an important pathway and SOST is involved, can we use this knowledge and develop novel molecules? And that's sort of been done. If we knock out SOST, so with an anti-sclerostin antibody, right? So sclerostin is the gene that encodes SOST. If you knock out SOST, can you get beneficial tissue changes? And this is in press at the moment. This is remosinab, which is an anti-sclerostin antibody that has gone through phase 3 trial, and it's the next bone drug. It's been shown to reduce fracture rates, increase bone mass in postmenopausal women. And the difference between this agent and, say, the traditional osteoporotic drugs is that this is an anabolic. Right? So most of the osteoporotic drugs are bisphosphonates, which are anti-resorptives, so they prevent bone resorption. This is actually an agent. By inhibiting SOST, enabling LRP5 to bind here, it's an anabolic agent. So we're sort of manipulating these mechanotransductive pathways via a molecule to generate tissue changes. So just to wrap up, it's important as therapists to understand the why and how all of this takes place, what pathways are involved, how cells respond to stimuli, right? Because it influences what are the important mechanical stimuli parameters. Right? So it affects our dose, the type of loading we introduce. We think of dose, we know that I talk about bone, but cells become desensitized to mechanical stimuli over time. Right? And we've shown this in the lab that if you introduce a mechanical stimulus to the skeleton, and so we did this with we introduced 360 cycles of exercise loading to an animal, all in one bout. In other animals, we broke that up into 90, into bouts of 90 cycles. So we had 360 cycles in one animal. The other animal, we did it 4 times 90 cycles spread out over the day. So they're getting exactly the same mechanical exercise. They're getting 360 cycles. One's just broken up by rest periods. And what you find is the ones that have the rest periods, they get much greater bone adaptation than the ones that get loading all at once. Because what happens over time, after about 100 cycles, bone cells desensitize. They become deaf to what's going on. Like, we've seen that stimulus. The molecular pathways have already responded to it, and they shut off. If you allow a rest period, then they resensitize, and you can load them again, and you get a much better adaptive response. Can we bypass the tissue forces and get novel stimuli to get a cellular response? So by knowing how certain cells, what they respond to, Can we introduce those stimuli without loading the tissue? And that becomes relevant for regenerative therapy, because if you've got a person who has an injury, well, not always can you load the tissue because you're worried about injuring that tissue further. So can we introduce some mechanical stimuli that the cells respond to without actually loading the tissue? Can you bypass even cellular forces? So can you get this sort of mimetics that look at the molecular pathways that are involved in mechanotransduction? Can we target some of the molecules involved, develop novel sort of antibodies to harness those anabolic effects? And they did that with the anti-sclerostin antibody. And then finally, can we optimize our timing? So if we know a patient is getting some sort of other therapy, well, is that therapy, is that pathway involved in mechanotransduction? And if so, can we couple mechanical loading with their other therapy to optimize our outcomes, whether it be PTH and mechanical loading, or whether it be the NSAIDs and COX-2? We know, that's on either side of the story, that we need to know the pathways involved. And basically what we're trying to do is work out how do we optimally load a tissue to sort of go from this is a rat lateral collateral ligament that's been injured, to the regenerative sort of state. So instead of getting this scar formation, can we get tissue to form like this by adding on mechanical loading in the right direction with other therapies to try and regenerate a lot of these musculoskeletal tissues? And just acknowledge the NIH for some of this work that I presented. And this is my daughter and her skeleton.